In today's lesson, we're going to be talking about the power rule. The goal of this lesson and future lessons is to come up with a set of rules so that we can calculate the derivative without having to take the limit and use our factoring techniques. So to start us off here, what we're going to look at is the derivative of a constant number. Now, if you take a look at the derivative of a constant number, visually that's fairly easy to see. If you take a look here, let's say we got a Cartesian plane here, and just as an example, let's say we have the function f at x is some constant value k. We'll just let k be any real number at all, doesn't matter. Let's assume here, let's say k is a positive real number. It looks something like this, right? You've got this flat line here. We can see visually that we already know that the derivative, the instantaneous rate of change at any point, the slope of the tangent line at any point here would be 0. I know this has a slope of 0. So I know my derivative at any point on this constant function is 0. Let's go ahead and just do this using our limit rules. So I'm going to take the limit. Now again here I'm using my alternative formula. If you missed that lesson, I'll link it in the top right hand corner. But as I approach my limit here, I'm going to take the limit as x approaches a. F at x is equal to k no matter what. F at a is also equal to k no matter what divided by x minus a. Now this is going to be the limit as x goes to a. K minus k is 0, and then you're dividing that by x minus a. Now, 0 divided by anything, before I even take the limit, right? Before I even take the limit, this divides out and becomes 0. Well, the limit as x approaches a of 0 is 0, and we're done. So therefore, we've proven that in general, if you have a constant function, its derivative is automatically 0. So we have this function f at x is defined to be x to the n, and we want to be able to find what is the general form of the derivative of this value here. Okay, so let's go ahead and try this out. I'm going to first use my alternative formula for the slope at a point here. This would be the limit as x goes to a of f at x minus f at a over x minus a. Again, if you've missed that formula, I'm going to link that video in the top right hand corner. You can check it out. Now, as I go here, I can take the limit as x approaches a. F at x is equal to x to the n. F at a will be a to the n, and divided by x minus a. Now, we're going to have to take a little detour here and take a look at a factoring property regarding this. So let's take a look. If you take x minus a and you divide that into this polynomial x to the n minus a to the n, let's take a look at what would happen here. Well, first of all, this first term would be x to the n minus 1. If I go ahead and go through long division doing this, this will be x to the n minus a times x to the n minus 1. Subtracting this, we end up getting a x to the n minus 1 minus a to the n, right? Those x to the n's will cancel. Now the next term here will be plus a x to the n minus 2. And then when I go ahead and multiply this out, we end up getting a squared x to the n minus 2. And watch when we subtract this here. Again, those leading terms will cancel. And I get here a squared x to the n minus 2 minus a to the n. And continuing on here, I'm going to put a plus a squared x to the n minus 3. And go ahead and doing my long division here, I get a squared x to the n minus 2 minus a cubed x to the n minus 3. And subtracting this up here, again, cancellation. And I think you can start to see the pattern that's emerging here. And then we would continue on in this manner. You'll keep going, doing this all the way down until what ends up happening here is you end up getting your last line ends up getting x to the a to the n minus a to the n, which gives you 0. This will continue on all the way down until we get to a to the n minus 1. If you notice the pattern here, when you sum the exponents, it always adds up to n minus 1. The exponent on this a is a 1, and adding these together, we get n minus 1. Exponent on this is a 2, and add that to n minus 3, you get n minus 1, and it'll continue on in that fashion. So therefore, what we have here is the polynomial x to the n minus a to the n divided by x minus a must equal this expression here. So let's sub that in for our fraction that we have on the left-hand side. Okay, so coming back to this question again, gave us a little more room here to work with. going to take the limit as x goes to a. Now we know this divides out nicely. It divides out into x to the n minus 1 plus a x to the n minus 2 plus a squared x to the n minus 3. Again, remember these all have to add up to be n minus 1 all the way down until we end up getting here a to the n minus 2 times x plus finally a to the n minus 1. Now we have here a polynomial. It's continuous. I can sub this value in. When I sub these in here, my first term will be a to the n minus 1. My next term here, if I sub in for x, I put in an a, we're going to get a to the 1 times a to the negative 1, which again will be a to the n minus 1. Again, we get a to the n minus 1 all the way down right to the very end, and you get a to the n minus 1. Well, how many of these terms are there? There's exactly n of them. This becomes n a to the n minus 1. Summarizing our results here, we now know that dy dx evaluated when x is a is going to equal n a to the n minus 1, or equivalently, f prime at a is going to equal n a to the n minus 1. Generalizing this for a random variable x, we have f prime at x is going to equal n x to the n minus 1. And that means that for a given function, f at x equaling x to the power of n, its derivative is simply a matter of taking that exponent, dropping it down, and subtracting 1. Let's take a look at some applications. So in our first example here, I want to go ahead and calculate f prime here. F prime at x, you're going to take the power, in this case the exponent's of 3, we drop it down, and then we subtract 1. 3 minus 1 is 2. So f prime at x is 3x squared. Let's take a look at the next one. So for the derivative here, again, you identify the exponent. The exponent here is a negative 2, so we drop that down, goes to the front as a coefficient in front. Then we subtract 1. If you take negative 2 and subtract 1, it becomes negative 3. And now the derivative is negative 2x to the negative third. Works the same for fractions. Let's say I want to find dy dx. The derivative here, you're going to take your exponent, which is a third, brings it out as a coefficient. Now you take a third and you subtract 1. Well, if I take a third and I subtract 1 from there, we're going to end up getting a third minus 3 over 3 is negative 2/3. So the exponent here is going to be negative 2/3. And therefore my derivative was 1/3 x to the negative 2/3. Let's try another. So same idea here. Exponent here is negative 4/3 this time. So the derivative is going to be negative 4/3 x. Now we take our exponent of negative 4/3 and we subtract 1. Well, negative 4/3 minus 1 is negative 7/3. And now my dy dx is negative 4/3 x to the negative 7/3. It works for irrational numbers as well. If I go to take my derivative here, this will be f prime at x. Take the exponent, in this case it's root 2, drop it down, put down your x. Now you just subtract 1, so you can leave it as root 2 minus 1. Would be the most efficient way to write it, and that's our derivative for this one. Continuing this on here, and this is x to the power of pi. Remember, pi is just a number, so we drop that down, and that becomes pi x to the pi minus 1. Becomes our derivative. We can also do this if we have a coefficient in front. If you have a coefficient in front, if you remember when we were talking about our limit rules, the coefficient can come out of the limit. Since your derivative is really just a limit, we can take that coefficient and pop it out front. So if I go ahead and take my derivative, the derivative is going to be 2. We still drop down the third, and this becomes x, and then a third minus 1 is negative 2/3. So my derivative, f prime at x, is going to be 2/3 x to the negative 2/3. And this becomes my derivative. Likewise, sometimes you'll get a question where it's not really written in exponential form. So if I want to find dy dx here, I'd like to actually express this first in exponential form. So I'm going to rewrite this in exponential form, in which case this will be x to the power of 4/3. And if you need a refresher on exponential form and with radicals, I'll link a video in the top right hand corner. You can check it out if you need to take a look at that. But now that I've written this in exponential form, the derivative here would be 4/3 x. We take the 4/3, subtract 1 from that, will give us, we left with a third. So dy dx is 4/3 x to the 1/3. Continuing on here, the same challenges. Sometimes you have to clean up your function before you take your derivative. So this is written in root form. If I write this in exponential, this would be x to the half over x to the 2/3. So now in this question here, again, I'm dividing with the same base. I can subtract the exponents. So this will be x to the 1/2 minus 2/3. And in which case here, this will be x to the 1/2 minus 2/3 will be negative a sixth. In which case here, I can go ahead and calculate f prime at x. And f prime at x, we drop down the exponent of negative 6, subtract 1, and we get negative 7 over 6. All right, continuing on here, same idea. We want to clean this up. But you'll notice here, this is written in with a positive exponent, but we can write it with our negative exponent so it matches our form, right? Because the form that we have here for our derivative, we have f at x has to equal x to the power of n. And notice our variable x is in the numerator. Well, I can easily rewrite this as root 10 times x to the negative 2. You'll see here. And now this is matching our original definition of our function to use the power rule. So now if I go ahead and calculate dy dx here, we're going to go ahead and drop down that negative 2, put the x down, and then subtract 1 from the negative 2, in which case we get negative 3. Typically, as you guys know, we put the minus 2 first, so this would be negative 2 root 10 x to the negative 3 for our derivative. All right, let's try some more. And sometimes you have to do a little bit of your exponent rules first. So in this case here, f at x is going to equal, before we go ahead and use our power rule, we're going to take power to a power, we multiply, this will be x to the 10, and now we can see quite easily f prime at x here will be 10 x to the power of 9. Okay, let's take a look at an application question here. We've taken a look at these sorts of questions before, right? Find the tangent equations, right? That's what they want us to find here. Find the tangent equation. Now they give us a curve, and the curve is y equals x root x. So the first observation to make here is I can write this as x times x to the power of 1/2. This is the power of 1. So putting this together, this is really just x to the power of 3/2. All right, so what's going on here? We have this function, x to the 3/2, and they want us to find the tangent equation, and this is a little bit different. They want us to find the tangent equation that's parallel to the following line. Well, tangent equation is a line. This is a linear equation as well. Two lines are parallel to one another if their slopes are the same. So we have to go about and find the slope of this line. Well, you can see here that 6x minus y equals 4. That's in standard form. If I put in slope-intercept form, we're going to get 6x minus 4. So I can see here the slope of this line is 6. So therefore, what I need to do is I need to find points on this curve where the slope of that tangent line at that point is 6. Well, how do you express the slope of a tangent on any point in the curve? That would be your derivative. So therefore, my original function is f at x is x to the 3/2. If I go ahead and calculate my derivative, this will be f prime at x. Using my power rule properties, this will be 3/2 x to the 1/2, subtracting 1. Now, this gives me a general form for the slope of the tangent line at any point on this curve. I want to find all of the tangent lines whose slopes are exactly 6. So set this equal to 6 and solve. Solving this here, we get 12 is 3, x to the 1/2. 4 is equal to x to the power of 1/2. In this case here, we can square both sides, in which case I get x equals 16. So therefore, there's exactly one point on this curve where the slope is exactly 6. What is that point? Well, that point is going to be what? I know the x value is 16, therefore the corresponding y value will be f at 16. Now notice here, I'm not subbing this into f prime, and that's a very common mistake that students make. We're subbing into our function f. I want to find the point on the actual function. I don't want to find the point on the derivative graphed function. So f at 16 is going to be 16 to the 3/2, which if you take a look here, this is going to end up being here the square root of 16 raised to the power of 3, which is going to be 4 cubed, which is going to be 64. So therefore, the point is 1664. Now to find the actual equation, the equation of that line is going to be y equals, we know the slope at that point is 6, so it's be 6x plus b. Subbing our point in here, we can go ahead and solve for b, in which case here I get b equals 64 minus 6 times 16, and that y-intercept is equal to negative 32. Putting this all together, the equation of the tangent line that is parallel to the line given in the question is y equals 6x minus 32. Okay, that concludes today's lesson. Review the power rule questions. I encourage you guys to rewatch the video and try to do all these examples on your own, right? Pause the video, try them out, see if you can get the correct answer. There's a good chunk of them here. We're looking at over 10 questions to try out, 10 or 11 questions to try out. Give it a shot. Make sure you're good with the power rule,